Western Europe is in the middle of a record-breaking heat wave. Some places have reached 111 degrees Fahrenheit. 6 countries have issued their highest-level heat warnings. People are losing their lives, and the reason might be more complicated than anyone could expect. France put most of the country under a red alert. The country's average temperature reached 86 degrees Fahrenheit. Not so extreme, but it's the average across the entire country day and night. In some places, temperatures climbed to 109 degrees Fahrenheit. It got so hot that 2 of Paris's most famous landmarks, the Louvre Museum and the Eiffel Tower, had to close earlier than usual. The buildings simply aren't designed to handle that kind of heat. More than half of France is under the highest heat warning. Tens of thousands of homes lost electricity. There's a massive risk of wildfires, and firefighters are already battling devastating forest fires. Since the heat wave began, at least 40 people have lost their lives in heat-related incidents. The rest of Europe isn't faring much better. The United Kingdom recorded one of its hottest Junes ever. Forecasters say that temperatures in certain places could reach 100 degrees Fahrenheit. Some cities have closed schools because classrooms became too hot. Power systems are struggling to keep up with all air conditioners and fans. Hospitals are treating more and more people with heat-related issues. Spain saw its highest average daily temperature since 1950. In May alone, 101 people in the country lost their lives because of heat. That's more than ever before for that month. Italy faces the same problem. Much of the country sits under the highest heat warning. The heat dries out the land. Some parts of Germany worry about drought. Local authorities have asked people to save water because supplies might run out quickly if the hot weather continues. The danger doesn't stop there. Dry grass and forests can catch fire much more easily during a heat wave. Some German cities have already banned barbecues to lower the risk of starting wildfires. The Netherlands has also warned people to prepare. Weather officials issued an orange alert. This means dangerous weather is likely to arrive. Temperatures could climb to 102 degrees Fahrenheit. Belgium faces almost the same forecast. Much of the country remains under an orange heat alert, with temperatures potentially reaching 99 degrees Fahrenheit. Scientists have warned about this for decades. As more greenhouse gases build up in the atmosphere, they trap more of the sun's heat, like adding another blanket around Earth. The extra heat has to go somewhere, and Europe has become one of the fastest warming places on the planet. In fact, on average, Europe is warming about twice as fast as the rest of the world. That means heat waves like this will become more common. They'll last longer and reach even higher temperatures. You might be wondering why this keeps happening to Europe. You'd think every part of the planet would warm at about the same speed. Instead, Europe is warming faster than any other continent on Earth. The whole planet is now about 2.5 degrees warmer than it was before people started burning huge amounts of coal, oil, and gas. Meanwhile, Europe has warmed by about 4.3 degrees Fahrenheit. Part of the answer is surprisingly simple. Europe has a lot more land than ocean, and land heats up much faster than water. When you walk barefoot on a beach during summer, the sand burns your feet, while the ocean right next to it still feels cool. Water can soak up a huge amount of heat without getting really hot. Land can't. Europe also stretches far into the Arctic, and the Arctic is changing incredibly fast. Snow and ice normally act like giant mirrors. They bounce a lot of the sun's energy back into space. But as temperatures rise, that snow and ice melt away. Underneath them, there's dark ground and dark ocean water. Those darker surfaces absorb much more sunlight, which creates even more warming. That extra heat melts even more ice, and this vicious cycle repeats again and again. There's another thing most people never think about. Europe has seriously cleaned up its air by cutting pollution from factories and power plants, and that's great news for people's lungs. But some of that pollution was kinda good. It reflected a bit of sunlight back into space. Now the air is cleaner and more sunlight reaches the ground. This effect isn't so powerful compared to greenhouse gases, but it adds even more warming. Besides, right now, a huge area of high pressure is sitting over Western Europe. Meteorologists call it a heat dome. Imagine putting a giant glass bowl upside down over a city on a sunny day. The hot air underneath can't escape very easily. At the same time, the high-pressure system pushes air downward. When you squeeze air into a smaller space, it gets hotter, like a bicycle pump gets warm when you use it. That high pressure also clears away clouds, so sunlight pours onto the ground from morning until evening. And then, there's one more piece to the puzzle. Recently, winds have been pulling even hotter air north from the Sahara Desert. Then the heat dome trapped that air over Europe, so the continent ended up with the worst possible combination. Hot air from Africa, non-stop sunshine, and a giant lid in the atmosphere keeping all that heat locked in place. We should expect the next 5 years to break even more heat records. What used to count as an extreme heat wave is starting to become a normal summer. Are Europe's cities ready for this? That's a big problem. Heat takes the lives of more people in Europe than floods, wildfires, or storms. The World Health Organization states that every year, more than 175,000 people across Europe pass away from heat-related causes. Yet, authorities still don't treat extreme heat waves like other natural disasters. They often react only after temperatures become dangerous. Unlike hurricanes or floods, many countries still don't have a clear long-term plan for dealing with heat. Luckily, it's changing. Last year, the United Nations worked out a new global plan that might help countries prepare for extreme heat. The main goal is to treat heat waves as a real disaster instead of just another hot summer day. But fixing the cities themselves is much harder. Europe spent centuries building roads, homes, and public spaces for a cooler climate. Some streets were laid out long before cars even existed. Nobody back then expected summers with temperatures above 104 degrees Fahrenheit, so nobody designed cities to handle them. So now they're filled up with dark roofs, brick buildings, concrete, and asphalt. All of those materials act like giant sponges for heat. They soak up sunlight all day, then slowly give that heat back after the sun goes down. That's why walking through the middle of a city on a hot evening can actually feel worse than standing in the countryside at the same time. Even after sunset, the heat has nowhere to go. In many places, downtown areas stay up to 7 degrees hotter than the neighborhoods around them. To deal with this issue, Paris wants to plant about 170,000 trees. It'll help create more shade. Marseille is ripping out pavement in some old public squares and replacing it with plants and grass. Other cities are painting streets with lighter colors, so they reflect more sunlight instead of soaking it up. Some are changing building rules so new homes stay cooler and don't depend so much on air conditioning. But so far, it's a bit like putting a bandage on a broken leg. The real problem hasn't gone away. Europe still burns huge amounts of oil, gas, and coal every day. Cars, airplanes, factories, and power plants keep sending greenhouse gases into the atmosphere. On average, one person in the European Union is responsible for about 10 tons of greenhouse gases every year, while the global average is only about 5.5 tons. In many cases, it's still cheaper to fly than to take a train. Cities still don't have enough cooling centers where people can escape the dangerous heat. Many new buildings could become unbearably hot in just a few decades. And many older people who live alone still don't get regular check-ins during heat waves, even though they're the most likely to pass away from them. The European Union plans to roll out a new climate strategy by the end of 2026. It's supposed to help countries prepare for more extreme weather. Alarmingly, the weather is changing much faster than Europe is, and every summer, that gap gets a bit bigger. Take a look at the map of Europe and find Spain and Portugal. These countries are connected to the continent, yet they seem to lie on a separate piece of land. This area is called the Iberian Peninsula, and right now, as you're watching this video, it's rotating clockwise, slowly moving closer to the rest of Europe. This movement is extremely slow, and of course, you wouldn't feel anything if you were standing there. But over time, this rotation could significantly change the geography of Europe. So, why is this happening? Several large and many smaller tectonic plates cover the planet. These are massive sections of the Earth's crust, about 60 miles thick, resting on the upper layer of the mantle. And these giant plates are constantly moving, not fast enough for us to feel, but relentlessly enough to reshape the entire planet over tens and hundreds of millions of years. So, why do they move at all? No one knows for sure, but the most popular theory suggests that when one part of a plate sinks into the mantle, it pulls the rest along with it. It's similar to a large iceberg. When one part goes underwater, another part rises. Of course, many other factors are involved, such as temperature and gravity, but let's not dive too deep. What matters is that the tectonic plates beneath our continents are always in motion. So, the Iberian Peninsula rotates clockwise because the African and Eurasian tectonic plates are slowly colliding. Thanks to this massive and chaotic process, it's difficult to see a clear boundary between these plates on the Earth's crust. Instead of a sharp line, the boundary bends and shifts, absorbing energy in some areas and releasing it in others, deforming the whole region. But you won't see this boundary on a regular map of continents and countries. The map of tectonic plates looks a bit different. They're much larger and lie beneath our continents. Some plate boundaries are even underwater. The Iberian Peninsula itself sits directly on the boundary between the African and Eurasian plates. But how fast are they moving toward each other? Take a look at your fingernails. They have something in common with these two tectonic plates, which move at about 4 to 6 millimeters per year. That's roughly the average speed at which your fingernails grow. So how did scientists figure this out? Thanks to large-scale research, specialists studied records of numerous earthquakes in the region, the geometry of faults during seismic activity, and also analyzed data from hundreds of GPS stations that track how our planet shifts by fractions of a millimeter each year. The analysis of all this data showed that the tectonic plate boundary behaves very differently on either side of the Strait of Gibraltar, which separates Europe from Morocco. In the eastern part of the strait, the Earth's crust acts like a buffer, absorbing the stress between the two plates. In the western part, this buffer disappears, and Iberia collides with Africa on one side and with Europe on the other. This uneven movement causes the entire peninsula to rotate. But what does this lead to, and why is it important for us to know? In 1755, a powerful earthquake struck off the coast of Lisbon. It partly destroyed the city and triggered a tsunami in the Atlantic Ocean. After that, there were many other smaller yet still destructive seismic events. Modern research helps identify the most dangerous zones along the plate boundary and allows scientists to assess earthquake risks better. Of course, there's still a lot of work to be done. To understand seismic activity fully, scientists need to know how the plates behaved in the past. The first high-precision satellite measurements only appeared around 1999. We don't know exactly how the plates moved millions of years before that, which makes reconstructing geological evolution extremely difficult. So right now, we're witnessing changes in the shape of continents. Are similar changes happening elsewhere? Absolutely. One of the most striking examples is the Great Rift Valley, which stretches from the Afar region down to Mozambique. The East African Rift System lies at the very heart of this massive valley. This is what scientists call the zone where the African continent is slowly breaking apart. Recent satellite images and geological studies have shown that the rift is expanding quite fast and will eventually reshape the entire region. But how fast exactly? About 7 millimeters per year. According to estimates, the entire process will take tens of millions of years. On a planetary timescale, that's relatively fast. But for us, there's no need to worry, at least for now. All of these geological changes may seem frightening. You probably imagine massive earthquakes, floods, panic, and destruction. Cities vanish, giant cracks appear in the ground, and chaos is everywhere. Yes, something like that will likely happen, but in reality, these changes will also bring many advantages. As the East African Rift System continues to split, an ocean basin will form, transforming the climate and environment of the entire region. Large areas of land will sink below sea level, and the overall sea level will rise. Essentially, this massive separation will give birth to an entirely new continent. New coastlines will appear, where people will build ports. New shipping routes will be created, significantly improving the region's economy. Access to water will transform agriculture and create many new opportunities for locals. Animals that never lived there before will appear, along with new species of fish and insects. Of course, competition for emerging resources will begin. Countries will redraw borders. There will be a lot of arguments and conflicts, which will lead to great tension. But this is not surprising. People always do this. To better understand what this process will look like, we can look at the past. Imagine a large landmass where people live and build civilizations. Then, over time, this land sinks underwater and separates a small piece of the continent from the larger one. This happened relatively recently in human history, even though most people don't know it. Take a look at Great Britain. Have you ever wondered why it's separated from the European continent? Now look at the North Sea. Thousands of years ago, there was no water here. Modern Britain was connected to Europe by a vast landmass called Doggerland. Around 12,000 years ago, the last major ice age was coming to an end. Doggerland was a region of gentle hills, wetlands, dense forests, valleys, and lagoons. Hunter-gatherers lived there. During different seasons, they moved across Doggerland, catching animals, fishing, and gathering nuts and berries. They lived there pretty well and comfortably for a long time. But around 6,000 years ago, these people were forced to abandon their homeland. When the Ice Age ended, massive glaciers began to melt. Sea levels rose dramatically. Water flooded Doggerland and forced people to leave. This was a long process and not a sudden surprise. The water level rose over many centuries. During this time, local populations migrated to what is now Great Britain and the Netherlands. But if Doggerland is completely underwater, how do we know it ever existed? Archaeologists and fishers discovered many artifacts in seabed sediments that indicate human presence. There were ancient bones and tools dating back 9,000 years. These discoveries sparked great interest among British and Dutch researchers, leading to large-scale studies of this submerged region. But here's the most interesting part of this story. In a way, when we look at Doggerland, we are looking at ourselves. What happened to people there is happening to us today. Global temperatures are rising, glaciers are melting, and sea levels are increasing. Over the next few thousand years, warming will likely intensify. Many land areas will be submerged. Hundreds of millions of people will be forced to migrate, and the world map will take on an entirely new shape. In any case, there's no need to panic. If those guys thousands of years ago managed to survive these changes and relocate to safer areas, then in the modern world, with advanced technology and global communication, large-scale human migration will be far more comfortable.
One day, the Mediterranean Sea will no longer exist. The Strait of Gibraltar, that narrow strip of water you can see across on a clear afternoon, will be gone, and Spain, Portugal, and Morocco will probably become a single unbroken landmass. This is not science fiction, this is geology. And despite it will only happen in a few million years, the process is already happening right now, beneath your feet as you watch this video. Let's talk about it. Imagine you're holding a giant puzzle. The Earth's surface is like that puzzle, broken into big pieces called tectonic plates. These pieces float on hot, gooey rock deep underground, and they very slowly move around. Now, Spain and Portugal, together called the Iberian Peninsula, are sitting on one of these puzzle pieces, and scientists have just discovered something remarkable. That piece is slowly rotating, like a clock's hand, but incredibly slowly. And here's the thing about a rotating puzzle piece. It no longer fits where it used to. If you tried to push it back in, you'd have to shave off the edges around it. It would be wobbly and imperfect, but eventually it would settle into a new position. The puzzle is never going to look the same again, and if you wanted to hold it all together for good, you'd reach for the strongest glue you have. And once it sets, what were two separate pieces become one single, larger, immovable chunk. That is exactly what awaits Spain, Portugal, and Morocco. Over millions of years, the slow rotation and the relentless pressure of colliding plates will push them together until they fuse into one continuous landmass. A new giant piece of the puzzle that will never come apart again. But let's back up a little, because to understand why this is happening, you need to understand what's actually going on underneath our feet. The Earth's crust is not one solid shell. It's cracked like the shell of a hard-boiled egg that you've dropped on the floor. Those cracks divide the surface into large sections, those tectonic plates we mentioned, and they're constantly on the move. Not fast enough to see or feel or even measure without very precise instruments, but they move. And two of the biggest ones, the African plate and the Eurasian plate, have been on a slow-motion collision course for millions of years. Right now, they're creeping toward each other at a pace of about 4 to 6 millimeters per year. That's roughly the length of an ant. Sounds like nothing, right? But add that up over 1,000 years and you've got about 20 feet, the length of a decent-sized yacht. Add it up over 1,000,000 years and you're talking about up to 3.5 miles of movement. The Earth doesn't rush. It doesn't need to. Now, if you open Google Maps and zoom in on the very bottom tip of Spain, you'll spot a tiny little strip of land jutting out toward Africa. That's Gibraltar, the narrow channel of water separating Europe from Africa. And when we say narrow, we mean it. At its tightest point, the strait is only about 9 miles. On a clear day, you can stand on the Spanish coast and see Morocco with your own eyes. Two continents close enough to almost touch, and getting closer every single year. Nobody alive today will ever see them merge, not our children, not our children's children, not anyone's for millions of generations to come. But we're here to think big, so let's keep going. The place where the African and Eurasian plates meet, just south of the Iberian Peninsula, has frustrated geologists for decades. Unlike most plate boundaries, which are sharp, clean, well-mapped lines, this one is blurry and complicated. The two plates don't just collide cleanly here. They grind, they overlap, they push sideways, and the result is a messy zone of stress and deformation that scientists are still trying to fully understand. To get a better picture, a team of researchers combined two types of data: readings from GPS satellites orbiting the Earth and records of earthquakes that have occurred across the region over recent decades. By looking at how the crust is being squeezed and warped at that boundary, they were able to map the underground stresses. And what they found confirmed something that had long been suspected but never clearly proven. The Iberian Peninsula is performing a slow, clockwise rotation. Here's why, and this is where it gets really interesting. Just east of the Strait of Gibraltar, there's a geological structure called the Gibraltar Arc. Think of it as an enormous underwater mountain range that curves in a wide arc, like a bent arm, connecting the mountains of southern Spain on one side and the mountains of northern Morocco on the other. The Baetic Cordillera runs through southern Spain, sweeping from the coast near Cadiz all the way to the Sierra Nevada. On the African side, the Rif Mountains in northern Morocco form the other end of this arc, and between them, mostly submerged beneath the sea, lies the arc itself. Now, this structure is not sitting still. The entire Gibraltar Arc is slowly drifting westward, toward the Atlantic, and as it moves, it stretches and curves, almost like a slow-motion wave rolling toward the ocean. And here's the crucial part. As it does that, it acts like a natural shock absorber. All that enormous pressure generated by the African and Eurasian plates grinding into each other, east of the strait, the Gibraltar Arc soaks most of it up. It takes the hit so that the rest of the Iberian Peninsula doesn't have to. The stress gets absorbed into the arc's own deformation rather than transmitted further inland. But west of the strait, the arc's protection runs out. There's no buffer, no shock absorber, nothing standing between the two colliding plates and the southwestern corner of Iberia. The African plate pushes directly into it. like pressing hard on one corner of a revolving door. And that uneven pressure is precisely what causes the whole peninsula to rotate clockwise. The east is somewhat shielded, the west is getting pushed, and the result is a slow, grinding twist that's been building for millions of years. Now, you might be thinking, okay, fascinating, but what does any of this have to do with my life? Fair question, but here's the thing. You might be closer to this than you think. The most direct way these tectonic forces make themselves known is through earthquakes. The southwestern part of the Iberian Peninsula, around Cadiz, Sevilla, and southern Portugal, is one of the more seismically active regions in all of Western Europe, precisely because of this pressure, and historically has already shown us what happens when that pressure gets released all at once. In 1755, Lisbon was hit by one of the most catastrophic earthquakes ever recorded. It leveled the city, killed tens of thousands of people, and sent a tsunami rolling across the Atlantic Ocean. That earthquake was a direct product of the exact same tectonic forces this research is describing. Beyond earthquakes, the movement shows up in subtler ways too. GPS satellites are now sensitive enough to detect that specific points on the Iberian Peninsula are shifting by a few millimeters every year relative to the rest of Europe. And the mountain ranges of southern Spain, the Sierra Nevada and the Beatic Cordillera, are still being actively pushed upward by this compression. They're technically still growing, just far too slowly for anyone to notice. The same goes for the Rif Mountains across the water in Morocco. The rotation is happening all around us. It's just that most of its consequences play out on a timescale that makes an entire human life feel like a single frame in an extraordinarily long movie. And the ending of that movie? The Mediterranean Sea gradually closes. Africa and Europe join at the western end. The Strait of Gibraltar disappears, replaced by mountains and rock and a continuous landmass stretching from Scandinavia all the way to the Sahara. It sounds almost impossible, but the forces making it happen are already at work. Right now, beneath your feet, one ant's length at a time.
A tsunami hitting major cities on or near the Mediterranean Sea and in the northeastern part of the Atlantic Ocean is not a matter of if, but when. It is scary and surreal to think that places like Cannes or Barcelona could suddenly get slammed by a huge wave, but the fact is, European coastlines are in active tectonic areas. Only about 10% of all tsunamis worldwide happen in the Mediterranean, and there have been at least 290 tsunamis in this area since 1600 before Common Era. Despite the relatively low number, this phenomenon has caused numerous devastating disasters throughout Europe's history. Back in 1755, an estimated 8.5 magnitude earthquake with an epicenter southwest of Cape St. Vincent triggered a tsunami that destroyed most of Lisbon, the capital of Portugal. About 40 minutes after the earthquake, this massive wave just slammed into the harbor in downtown, racing up the Tagus River. The phenomenon was so fast that several people on horseback had to gallop to higher ground to avoid getting carried away. And this was just the beginning of a nightmare, with two more terrifying waves hitting Lisbon right after. A disaster like this is similar to what we see in the Pacific Ocean several times a century, but in the Atlantic, it's very rare. This type of major tsunami is expected to happen every 3 to 5 centuries, but now it could happen tomorrow. Marseille in France, Chipion in Spain, and other cities are on the list of important locations that could be flooded soon, with a roughly 100% chance of being hit by a tsunami in the next 30 years. Statistics show that the wave will probably be more than 3 feet high. I know, it doesn't sound like much, especially since when we think about tsunamis, we imagine terrifyingly tall waves, like the one that hit Lituya Bay in Alaska. In that case, the wave was over 1,700 feet tall. But we must remember that even waves only 19 inches high can be dangerous to swimmers, because it's not the height of the tsunami that matters, but also the flow and movement of the water. Not to mention the flooding, which can damage beaches, harbors, and streets. If the coastline has a small harbor and the waterfront is exceptionally low, like Cannes, this natural disaster might be much more dangerous. Tsunamis around 6 feet high can lift cars off the ground, while smaller waves can create walls of water traveling at 40 miles per hour. Plus, there are these smaller events that might not wreck everything, but still can cost a ton of money. For example, large sandbars that move around on the ocean floor, like sand dunes shifting in deserts. They can mess up pipelines or deep-sea cables for internet and communications, and that ends up costing businesses and governments millions of dollars. That's why organizations like UNESCO are worried about the possibility of a dangerous tsunami hitting Europe soon. So they're doing everything they can to prevent apocalyptic scenarios, like what happened in 2004 when an earthquake off the coast of Sumatra, Indonesia, caused waves over 100 feet high in coastal communities, resulting in over 200,000 lives lost. And let's not forget about 2011, when an earthquake off the coast of Tohoku, Japan, triggered a tsunami that reached about 6 miles inland and caused a major nuclear accident at a power station along the coast. Over 16,000 people lost their lives in that tragedy, and the event resulted in billions of dollars in infrastructure damage. These disasters were huge wake-up calls, and we've come a long way since 2004. We're much safer today, largely because the tsunami warning system is highly effective at quickly detecting this dangerous situation. Unlike many other natural phenomena, a tsunami can be anticipated. We may only have a few minutes to act, but if we all know what to do, many lives can be saved. And in most parts of the world, sirens are commonly used to alert people to tsunamis. To sound the siren as early as possible, initial tsunami alerts usually rely only on seismic data. First, specialists receive information about an earthquake. Seismic waves travel about 100 times faster than tsunamis, so they have enough time to analyze the data and see if the earthquake might have generated a tsunami and whether they should issue an initial tsunami alert. At U.S. warning centers, for example, scientists typically issue initial alerts within 5 minutes of an earthquake. If a tsunami is suspected, these alerts may also include information about wave arrival times, recommended actions, and potential impacts. But sounding the alarm is not enough. To save lives, coastal communities also need to be trained to respond fast and in the best way possible. That's why UNESCO produced this program called Tsunami Ready, aiming to train people living in coastal areas at risk on how to act in case of a tsunami event by the year 2030. The idea is to help communities stay safe by teaching them how to protect their livelihoods and safeguard their homes. Being recognized as Tsunami Ready by UNESCO doesn't mean a community is tsunami-proof, of course. It's more like a recognition that they have adopted all possible measures to mitigate tsunami risks. So authorities are helping communities to prepare themselves by installing evacuation signs, establishing security procedures, and creating plans to warn tourists. Like Spain, which distributed tsunami warning signs along the entire coastline, as well as signs showing evacuation routes to higher ground. And Spain better be prepared. I mean, only 7 tsunamis have hit the country since the year 365, so it's difficult to predict the effects of such an event. But they could be devastating, considering that Spanish coastal areas are so economically important. There's also a danger zone in the Averroes Fault, beneath the Barents Sea. If an earthquake happens at this point, people will have only 21 minutes to escape a tsunami. UNESCO has also established 12 tsunami warning centers, which cover Europe as well. This initiative involves 5 centers located in the Mediterranean and Northeast Atlantic regions. These centers can save thousands of lives because they monitor ocean disturbances 24/7. Then, after analyzing the threat, they send out messages based on the event's potential to cause a tsunami. The intensity scale ranges from no effect to completely devastating. And by that, they understand that nearly all brick buildings could be demolished by waves, and even the most reinforced concrete structures could suffer heavy damage. Now, so far, we have mostly talked about tsunamis caused by earthquakes along converging tectonic plate boundaries. In fact, earthquakes have accounted for over 80% of tsunamis since 1900. But tsunamis can also result from landslides, volcanic eruptions, and even meteorite impacts. Experts are also worried that with the current changes in climate, we might see more of meteotsunamis popping up in the Mediterranean. These ones are triggered by freaky weather conditions and can mess with any coastline that's got a shallow seafloor. They might not be as huge or famous as the earthquakes ones, but they can still cause significant property damage and put people in danger. For instance, in 2006, a meteor tsunami struck the harbor of Ciutadella on the Spanish island of Menorca. Yachts were tossed into each other and later stranded on the harbor floor as the water receded, resulting in tens of millions of euros in damage. Unfortunately, meteor tsunamis in the Mediterranean tend to be stronger during summer, so if you're planning to spend your vacation in Europe, stay alert for any signs of dangerous waves. If you suddenly encounter a tsunami moving in your direction, remember this is the time to react. Move to higher ground as far inland as possible. Pay special attention to any emergency alerts and information, and follow the guidance of local authorities. Most importantly, do not wait around taking photos. Leave the area as soon as you notice any signs of this danger event, or if you hear an official tsunami warning. Hey, stay safe. Well, scientists have just reconstructed one of the biggest volcanic eruptions in Earth's history, and the more they dug into it, the worse it got. Over 350,000 years ago, the center of New Zealand's North Island looked completely different. The mountains we see today weren't there yet. The climate was colder, and the region was literally stuck in an ice age. Winters were harsh, and temperatures stayed low year-round. Everything looked calm and quiet, well, on the surface. Underground, something was building and building until it snapped. A supereruption hit the Taupo volcanic zone, the Whakamaru eruption, one of the biggest ever recorded on Earth. Now, it wasn't a single mountain that produced it. It was a whole volcanic system stretching from Wakari White Island in the north toward Ruapehu in the south. A weak zone in Earth's crust was getting stretched and broken at the same time. One force was pushing magma up, another was pulling the land apart. That combo powers this region even today, but back then it got extreme. The eruption blasted so much material that ash spread across huge parts of New Zealand. In some areas, it was so thick that it buried the land under layers of volcanic rock and debris. It was like dumping miles of powdered stone over a country. Today, that same zone hosts hot springs, bubbling mud pools, and steam vents. And all this sits on the top of the same, if a bit quieter, system. The Taupo volcanic zone has been active for about 2 million years, having produced at least 4 supereruptions. Those weren't small events. On the Volcanic Explosivity Index, they hit level 8, which is, so far, the maximum category. We've only had a few dozen such eruptions on Earth. The most recent one was the Aroa Nui eruption about 25,300 years ago. That one was even bigger in volume and created what is now Lake Taupo. In other words, Whakamaru wasn't a random disaster. It's what this volcanic system does from time to time. Supereruptions are still one of the hardest problems for scientists. Because how does a huge amount of magma sit underground, build up, and then just explode almost at once? To figure that out, researchers read the leftovers, ancient deposits. There are 2 main types of those. One is flow deposits, left by fast-moving avalanches of superhot rock, gas, and ash called pyroclastic flows. All that mass rushes along the ground like a burning flood and later solidifies. The other kind of evidence comes from fall deposits. Those are lighter materials like ash, crystals, and volcanic glass. They get blasted high into the air and then rain back down to the ground. Now, the problem is time. Most of these deposits don't survive. They get eroded, buried, and broken apart. What's left is often scattered across huge distances. The Whakamaru supereruption left exactly this kind of mess behind. huge pyroclastic flows form thick layers of dense volcanic rock across the Wakamaru and King Country regions. Farther out, ash and pumice spread much wider, covering large parts of the North Island and even reaching into sections of the Pacific Ocean. To piece all the traces together, researchers first had to track down where the fragments actually came from. They built a database of volcanic deposits and matched them using a chemical signature. You can find it locked inside tiny bits of volcanic glass. Each eruption leaves a slightly different chemical mix. Using that method, scientists checked more than 30 sites across New Zealand and the South Pacific. And even though the samples were spread so far apart, they all matched the same source, the Wakamaru supereruption. So, finally, researchers could piece together what happened during one of the biggest eruptions in Earth's history. At the start, the central North Island likely had a large lake in the middle of it, similar to modern Lake Taupo. Then, magma broke through the surface right into that water. That's where things escalated fast. When magma hits water, the water instantly turns into steam. That can make an eruption extremely destructive, and it's probably what kicked off this one. At first, one huge magma chamber was likely feeding the eruption, but soon the situation changed. The eruption continued, and the lake was destroyed and filled in by volcanic material. And once the water was gone, the style of the eruption shifted. It became drier and more direct. And underground, something even bigger was happening. Instead of one magma chamber slowly emptying, the system split into numerous active zones. At least 5 separate magma bodies may have started erupting at the same time. The ash output became extreme. Most of the North Island and even distant Chatham Island ended up under roughly 12 inches of volcanic material. Closer to the source, up to 15 feet of deposits covered the ground in some regions. Then came the pyroclastic flows, fast-moving currents of superheated gas and rock. Near the eruption zone, they left behind deposits hundreds of feet thick. When you add everything together, the numbers are hard to picture. The eruption blasted out roughly 550 cubic miles of material. If you spread it evenly across all of New Zealand, the entire country would end up buried under about 30 feet of volcanic debris. But the scariest thing is that the Taupo volcanic zone is still one of the most powerful volcanic systems on Earth. Supereruptions like Wakamaru are rare, but the system has produced many smaller eruptions too, and those are capable of reshaping large regions too. That's why this research matters not only for geologists. We must understand how these eruptions switch from single-source magma to multi-chamber catastrophe. This way, we'll be able to figure out what such a system is capable of doing in the future. And New Zealand isn't the only place where scientists worry about giant volcanic systems. One of the most famous examples is Yellowstone in Wyoming, Montana, and Idaho. Some experts think it might be overdue for a massive eruption. The last one happened around 70,000 years ago, according to the U.S. Geological Survey. And the last true supereruption occurred about 640,000 years ago. And yes, the volcano is still active, even though not in the imminent disaster way most people imagine. You can see that activity right on the surface. The Grand Prismatic Spring is the biggest hot spring in the U.S. and the third largest in the world. Its famous bright colors come from bacteria living in different temperature zones around the spring. The water itself hits about 158 degrees Fahrenheit. This spring is boiling, and volcanic activity is what's driving this process. The magma system below Yellowstone is massive. It may be even larger than we thought earlier. If it fully erupted one day, it could release around 2,500 times the energy of Mount St. Helens, and that eruption was a devastating event. In 1980, A 5.1 magnitude earthquake triggered the north side of the mountain to fall away, which created the largest debris avalanche ever recorded. The blast flattened about 230 square miles of forest and took the lives of 57 people. Anyway, all that underground activity doesn't mean Yellowstone is ready to blow tomorrow. In fact, it gets about 700 to 3,000 small earthquakes every year, and most are so weak that people don't even feel them. It's just the ground constantly shifting and adjusting. But if a full supereruption ever happened in that region, it would be a full-blown disaster. First, pyroclastic flows would rip through parts of Montana, Idaho, and Wyoming. Then the ash would start falling. It would spread across the entire U.S. Roofs could collapse under the weight of all that heavy ash in some areas. Air quality would drop, and water systems would get contaminated. Such a chain reaction could trigger a global food crisis, but it's just a hypothetical situation at the moment. We should remember that even though supervolcanoes are terrifying, they're rare. It's often the smaller volcanoes we should look out for. It's 9:59 a.m. when a man is jolted awake in his bed by a powerful, mysterious force. While he's trying to figure out what's going on, a giant 100-foot-tall column of water is already surging toward his hometown. In 20 minutes, most of his friends and family members will lose their lives when a sky-high wall of water sweeps away buildings, trees, and cars. And it can happen to you at any given time. It's the day after Christmas in 2004. Thousands of tourists from Europe and America are enjoying tropical beaches in Thailand, Sri Lanka, and Indonesia when a powerful undersea earthquake strikes off the western coast of northern Sumatra, Indonesia. It's a 9.3 magnitude earthquake, the most powerful ever recorded in Asia. It triggers one of the largest tsunamis in history, the Boxing Day tsunami, which will take the lives of 230,000 people within a few hours. The city of Banda Aceh in Sumatra, Indonesia, home to 260,000 people, is the closest to the earthquake's epicenter. In less than half an hour after the quake, huge 10-story tall waves crash into the city. More than 60,000 people lose their lives immediately. The destruction is so severe that almost no one in its path survives. Next, the tsunami hits Thailand. The waves, rushing at a mind-boggling 500 miles per hour across the Indian Ocean, reach the shores of Phang Nang and Phuket about 90 minutes later. Despite such a significant time gap, both locals and tourists are caught totally off guard. Many beachgoers even walk out onto the beach, curious about the strangely receding sea, only to be overtaken by a towering wall of water. Nearly 5,400 people, including 2,000 foreign tourists, won't survive that day in Thailand. An hour after Thailand, the tsunami hits southeastern India near Chennai. Debris-filled waves push miles inland, taking the lives of more than 10,000 people. Sri Lanka faces even worse devastation. The island will lose over 30,000 people, and hundreds of thousands will become homeless. The tsunami's incredible strength is evident even far away. 8 hours later, it claims its last victims in South Africa, 5,000 miles from the quake's epicenter. There, rogue waves catch swimmers off guard. Researchers from NOAA's Center for Tsunami Research explain that the destruction was due to the sheer power of the earthquake. It originated from a megathrust fault. That's where heavy ocean plates dive beneath lighter continental plates. These faults are the largest in the world and lie underwater. The 2004 earthquake ruptured a 900-mile stretch of the Indian and Australian plates, 31 miles beneath the seafloor. Plus, instead of one quick jolt, the quake lasted for 10 minutes and released an unimaginable amount of energy. During the shaking, massive sections of the seafloor moved upwards by 130 feet. That's a lot. Such a sudden movement set colossal waves rippling across the ocean. Imagine it like dropping a massive pebble into the water. The thing is, tsunami waves aren't like those surfing waves you may imagine. No, they look like a fast-moving whitewater river that floods everything in its way. If you get caught in those raging waters, it's almost impossible to survive. If the powerful currents don't pull you under, floating debris will. That's the reason why, during earthquakes, there are usually many injuries and fewer lives lost. With tsunamis, it's the opposite. There's way fewer injuries than fatalities because it's too hard to survive. Catastrophic tsunamis like the one in 2004 are rare. That's why India and Sri Lanka had no record of such disasters. This lack of experience, combined with the absence of warning systems, made the consequences of the disaster even more tragic. People didn't feel the earthquake because they were far from the epicenter. And with no natural warning signs, no official alerts, and no history of tsunamis, the waves that hit crowded coastlines had devastating effects. By the way, the Pacific Ocean, the largest ocean on Earth, is where most earthquakes and tsunamis occur. Locally damaging tsunamis strike somewhere in this ocean about once every 1 to 2 years. 76% of the recorded fatal tsunamis happened in the Pacific, and 99% of tsunami casualties are caused by local or regional tsunamis, which occur more often and hit quickly. But then a question arises: could a tsunami as devastating as the Boxing Day one happen again? Unfortunately, the answer isn't very straightforward. A warning system has indeed been established in the Indian Ocean. Its goal is to alert coastal nations of potential tsunamis. But human behavior is still a critical challenge. This became clear during a real-life test in 2012. That's when many residents of Banda Aceh, Indonesia, simply ignored evacuation towers after a tsunami warning. People never seem to learn, huh? The Indian Ocean Warning Network uses undersea pressure sensors placed near tectonic plate fault lines. These sensors detect any changes and transmit data to surface buoys, which then send it via satellite to control centers on land. Authorities analyze the information and decide whether to issue warnings and evacuate at-risk areas. Aceh, located on one of the world's most active fault lines, implemented additional safeguards. They installed sirens in coastal cities, and people get alerts on their cell phones. Plus, there are evacuation towers, reinforced concrete structures capable of holding 500 people. They are special safe zones. Authorities did test how well prepared people were. In 2009, 18 Indian Ocean countries participated in an evacuation drill, simulating a large earthquake. Thousands of coastal communities took part in this drill, and officials concluded that the exercise had been a success. Fast forward to the system's first real test in April 2012. An 8.6 magnitude undersea earthquake west of Aceh triggered tsunami warnings. And even though there were no significant waves, the whole situation revealed critical flaws. Many residents ignored evacuation towers, choosing instead to flee by car or motorbike. This led to citywide traffic jams, with people getting stranded in areas vulnerable to a potential tsunami. It was chaos. Some residents even went back to the beach to look for the signs of a tsunami, which is a life-threatening mistake. So apparently, there is still a lot of work to do when it comes to tsunami survival. But what you need to know by heart is the signs of an impending tsunami. First of all, it's severe ground shaking. Strong earthquakes near coastal areas can generate tsunamis. If you notice that water on the beach starts to recede at an alarming rate, exposing the ocean floor, reefs, and stranded fish, run. Then there might be unusual ocean sounds. Keep in mind that a loud roaring noise, resembling a train or jet engine, may accompany an approaching tsunami. If you notice any of these warning signs, do not wait for official evacuation orders. Leave low-lying coastal areas immediately and move to higher ground as fast as possible. If you're at home, make sure your family members know about the tsunami and follow official guidance. You should remember that locally generated tsunamis may strike within minutes. You have to act quickly. If it's a distant tsunami, you may have more time to evacuate. If you don't have an opportunity to move inland, hide in high reinforced concrete buildings. Avoid staying in small buildings or homes in low-lying areas. If you're on a boat, stay offshore. Tsunami activity isn't as dangerous in deep water, So avoid returning to port during a tsunami warning. If you're already in port, check with harbor authorities for guidance. If it's possible to move to deep water, do it in an orderly manner. It may be safer for small boat owners to leave their vessel and move to higher ground. And always, always prioritize moving to higher ground over saving your belongings. If you live in a coastal area, you can take some measures to protect your property in advance. Since most tsunami waves are under 10 feet, you may consider elevating your house. It can reduce damage. You can also consult an engineer to assess and reinforce your home. And finally, don't forget to protect outbuildings too, and create fences that will allow animals to reach higher ground. Around 2,500 years ago, an earthquake completely changed the course of one of the largest and most famous rivers on the planet, the Ganges. Now, it's normal for rivers not to sit in one place, so if you live next to one, it could also just disappear without a trace or flood the whole city one day. In the case of the Ganges River, a supermassive earthquake became the reason for this dramatic change. Scientists say it might happen again, and it would be a huge problem for millions of people who depend on this river. The Ganges River starts as small streams in the Himalayas and travels a long way, over 1,500 miles. Along its journey, it meets other big rivers before all the water flows into the Bay of Bengal. The Ganges has the largest delta in the world among all rivers. Just like many other rivers in the region, it slowly changes its path over time. These changes, if they happen when a river wears away its banks, usually takes a long time, sometimes decades. Scientists have discovered that the Ganges-Brahmaputra river system has shifted several times over the last 6,000 years. When they looked at satellite images of the Ganges Delta, they noticed something interesting. There was a crescent-shaped dip in the ground about 28 miles away from where the river is flowing now. This depression was over 1 mile wide and stretched for many miles. They thought it might have been an old main channel of the Ganges River a long time ago. In 2018, the team decided to visit the area to check it out for themselves and take samples to learn more about it. While driving back home, they noticed a pit where someone was digging dirt to create a pond. The next day, they planned to fill it with water, but the researchers spotted something strange in the dirt. There were vertical bands of light-colored sand mixed into the darker mud. These special layers are clues from the past. They show that an ancient earthquake made sand and water shoot up from below the ground and created sand volcanoes that were trapped in time. The scientists studied the sand and mud and figured out that these earthquakes happened around 2,500 years ago and were strong, with magnitudes of 7 to 8. The epicenter was over 110 miles away from the main stem of the river, but it was powerful enough to displace it. It could have affected around 140 million people. The Ganges-Brahmaputra system is close to spots where Earth's tectonic plates meet, so earthquakes happen here often. There's no danger right now, but scientists think that another massive earthquake could happen in the next few hundred or thousand years. It could threaten up to 170 million people. That's about half the population of the U.S. No one can predict exactly when an earthquake will happen or how strong it will be. Learning how earthquakes in the past moved rivers helps scientists figure out patterns and make guesses about similar events in the future. This knowledge could help us prepare better and create safety plans before another big earthquake strikes. Now, the Ganges isn't the only river at risk. The Yellow River, the Irrawaddy River, and rivers in the United States, like the Klamath and San Joaquin, all face similar dangers. The mighty Mississippi River has also switched its path many times over the last 7,000 years. Right now, there's a huge system of dams and barriers called a control structure in central Louisiana. This structure's job is to stop the Mississippi from spilling over its banks and joining a nearby river. But scientists think that, in theory, these barriers wouldn't handle mega floods. So, the Mississippi could break free and change its course again. This would cause massive problems, especially in southern Louisiana. One of the recent examples when a river changing its course caused disaster was the Kosi River in India. In August 2008, over just a few days, the river's path shifted by almost 60 miles, which is a huge change. Floods happen in some parts of the state rather often, but they hadn't seen such strong ones in over 50 years. They affected around 1,000 villages and 3 million people, and about 1 million people had to be evacuated to safety. Since many of these people hadn't faced floods in so long, they weren't ready to handle it quickly. It caused even more damage to their homes and lives. Scientists have been trying for decades to figure out what exactly makes rivers suddenly change their course. A new study explains that two things work together to make a river to do it. This process is called avulsion. First, there's the setup, which is like building up tension before something big happens. Over time, sediment, sand, dirt, and other stuff carried by the river gets deposited in certain places. It either raises the river above the land around it or makes a nearby slope steeper than the river's current path. Then there's the trigger, which is like the final straw that makes everything happen. This trigger could be a big flood, an earthquake, or even something like a pile of logs blocking the water. Now, researchers looked at satellite images of about 170 cases of avulsion from the past 50 years. They noticed these events happen most often near river mouths and near mountains. Rivers were about 3 times more likely to change course in these places than in the areas between them. They also studied 58 river channels in detail, using super clear maps to measure super elevation. That's how high the river is compared to the land around it. They also measured slope advantage. That's how steep a new path might be compared to the river's current one. They found that near mountains, rivers often pile up so much sediment that they become super elevated and spill over. But near river mouths, like in deltas, rivers need a steep slope advantage to break through the mud and form a new path. These two factors work together like a seesaw. If one is stronger, the other doesn't need to be as strong for an avulsion to happen. To figure out where a river might go if it changes course, the researchers created a smart computer algorithm. This tool uses maps to measure the terrain's steepness and the river's flow to predict where the river might move. They tested it on 10 past avulsions, and it correctly guessed the path every single time. Scientists hope they could use these findings to protect people living near rivers from sudden floods. Rivers changing course played a big role in creating one of the first organized administration systems in the world. Scientists found clues for this in the territory of ancient Mesopotamia. This name means the land between two rivers, and it was between the rivers Tigris and the Euphrates. People living there relied on these rivers for water, food, and transportation. Scientists wanted to figure out how these sudden changes in these rivers affected ancient people. To do this, they used two kinds of maps. The archaeological maps show how ancient cities grew over time, including what types of buildings people built. Certain buildings, like big palaces or city walls, could show when each city first had an organized administration. The second kind of map showed where the Tigris and Euphrates rivers flowed long ago. They often shifted, sometimes slowly, and sometimes very quickly and dramatically. Around the year 5000 BCE, Mesopotamia started to become drier and farming became harder. Farmers had to grow their crops near rivers, where they could use the natural floods to water their fields or dig little channels to bring river water to their plants. Because farming was so important, towns and cities grew near the rivers too, so people could stay close to their food. But when a river suddenly changed its course, people didn't give up. They worked together to dig long canals to bring water from the new river path back to their fields. The canals helped them get water again, and the administration buildings showed they were organizing as a community to solve big problems together.
The snowpack over your head splits in two right in front of your eyes and starts tumbling down in the frozen slope to its resting place far, far below. Anything in its way is crushed under the immense mass of snow and debris. You're witnessing an avalanche, one of the most dangerous natural disasters. But what if I tell you about another kind of avalanche, no less blood-chilling than the mountain one? And the most bizarre thing about it is that it occurs underwater. Underwater avalanches are powerful and disastrous natural phenomena, often much more dangerous than land ones. They have the potential to wreak havoc on the entire planet, leading to catastrophic consequences. The most alarming thing? They occur all the time under the surface of the ocean, impossible to see, predict, and extremely difficult to measure. Such avalanches can get 100 times larger than land ones, and they pose a great risk to the world's communications, capable of leaving the entire planet without the internet. But we'll talk about it a bit later. First, let's go 60,000 years back into the past. We're near the northwest coast of Africa, ready to witness the colossal scale and devastating impact of a ginormous underwater avalanche. It started as a quite small underwater landslide in the Agadir Canyon. At first, it was just 0.35 cubic miles of material. But in no time, this mass increased more than 100 times in size while traveling across the Atlantic Ocean floor. As the avalanche sped up and grew, it picked up gravel, sand, rocks, and mud. It carved a devastating path through one of the world's largest submarine canyons, wiping out all forms of animal and plant life on its way. The disastrous flow was so powerful that it literally eroded a 250-mile stretch of the canyon, cutting hundreds of feet into its sides and damaging a total area of 1,740 square miles. That's the area of more than 3.5 New York cities. As for the force of the flow, it was so immense that it propelled massive boulders up the canyon walls to heights of up to 430 feet. Before scientists discovered the evidence of this catastrophic event, they had seriously underestimated the scale of destruction caused by submarine avalanches. By the way, these devastating catastrophes can start not only far away in the ocean, but also at estuaries. Let's go back to 14 January 2020 and see for ourselves. A turbidity current, a rapid, downhill flow of water containing a lot of sediment, rushed more than 680 miles from the Congo River estuary in the deep sea. This current appeared due to two factors: terrible flooding along the Congo River in late December 2019 and unusually large spring tides. This resulted in an avalanche of sand and mud. Its volume was equivalent to 1/3 of all the sediment produced annually by all the rivers in the world. This sediment avalanche accelerated, increasing in speed from 17 feet per second in the upper part of the Congo Canyon to 26 feet per second when it reached the end of the channel, almost 700 miles away from the coastline. This route made it the longest avalanche of sediment ever measured on our planet. 2 days later, the flow reached the deep ocean. The avalanche broke 2 seabed telecommunication cables, cutting internet data speeds all the way across West, Central, and South Africa. Now, before this disaster, scientists considered that measuring powerful deep-sea avalanches was impractical. But the sediment flow in the Congo Canyon could be monitored directly, finally allowing researchers to assess how major river floods connected to the deep sea. They also concluded that how often underwater avalanches occurred depended on where the observer was. Seafloor canyons that are close to river mouths can experience several tiny avalanches per year. Other systems, far from river discharges like the Agadir Canyon, can only have one monster of an avalanche every 10,000 years or so. You're likely wondering, what can trigger an avalanche under the surface of the ocean? Well, earthquakes, typhoons, high tides, river floods, and even volcanic eruptions. And due to our changing climate, such events become more and more frequent and intense. At the same time, these triggers don't mean that an avalanche is bound to happen, nor do they relate to the scale of the event. See for yourself. In 1755, a powerful earthquake hit the coast of Portugal, wiping out large parts of Lisbon. Tens of thousands of people lost their lives during that disaster, but it only triggered a tiny underwater avalanche. And in 1929, a large earthquake off the coast of Newfoundland, Canada, triggered the largest underwater avalanche ever recorded. The flow traveled at a speed of 42 miles per hour, carrying boulders, sand, and mud.
It snapped 11 seabed cables on its journey downhill. The avalanche was so powerful, it produced a tsunami that claimed the lives of 28 people along the coastline. Now, submarine avalanches are totally invisible because they happen deep under the ocean surface, which makes them extremely hard to study. But we must find a way because these flows are super important. They transport sediments, nutrients, and even pollutants across the ocean floor. So, a research team from Liverpool decided to unravel this mystery. Over the last 40 years, they've collected more than 300 samples from the ocean floor. Combined with seismic and bathymetric data, which is a fancy word for ocean mapping, they managed to reconstruct a massive submarine avalanche. It was the first time an underwater avalanche of this size was mapped out. An even cooler thing, the event itself started off pretty modestly, but it quickly evolved into a colossal avalanche that grew to more than 650 feet tall. To put that into perspective, imagine a skyscraper-sized avalanche zooming from Liverpool to London, cutting a trench 100 feet deep and 9 miles wide. Then it spread out over an area bigger than the UK, covering it with several feet of sand and mud. That's like burying a whole country. These findings are actually a big deal because they show that even a small underwater landslide can turn into something massive and super destructive. But that's not the worst. Think about undersea internet cables, which are essential for global communication. There are more than 550 active seafloor cables around the world. Their combined length is a whopping 870,000 miles. That's enough to wrap around our planet 35 times. When a submarine avalanche breaks seafloor cables, the effects are usually super expensive and devastating. For example, in 2006, an earthquake in Taiwan triggered underwater avalanches that cut loads of seafloor cables connecting Southeast Asia with the rest of the world. The largest internet operator in China had a 90% loss of traffic to the USA at the peak of the event. As for Taiwan itself, it experienced between 74 to 100% loss in traffic to neighboring islands. So now you probably get why we need to learn more about this natural phenomenon. Luckily, researchers at Tulane University have found a way to study it in 3D. Previous studies only looked at submarine avalanches in 2D, which didn't give the full picture of how they actually behaved. The new research focused on how underwater flows interacted with mini basins, natural features on the ocean floor that look like shallow bowls. Despite being called mini, these bowls can be huge, up to 4 square miles. When turbidity currents flow into these mini basins, they don't just stop. No, they hit the far side and curl back around like water eddies in a stream. These swirling flows move the sediment around before it settles on the ocean floor. The size of the mini basin and the speed of the flow can change how the current behaves. If the basin is big and the current is slow, it starts to fill up with sediment. But if you crank up the flow speed or shrink the basin, the current starts to overflow, spilling over the basin. To study all this, the researchers created a mini version of a mini basin in a pool and used different speeds of flow to simulate turbidity currents. They even made their own sediment mixtures to see how different sizes of particles would behave. In the end, they managed to mimic real-life ocean conditions, but on a smaller, manageable scale. Pretty cool, huh? Back in the day, from 774 to 775, Earth got hit with a mega blast of radiation. This crazy burst of energy left its mark. 3 rings from that year show way too high levels of radioactive stuff. But what exactly caused it? Scientists are inclined to think that the reason was a solar flare. Some folks think maybe a massive supernova caused the radiation blast. But astronomer Phil Plait says that if that had been the case, it would have had to be less than 1,000 light years away and would have been crazy bright. But there's no record of that happening. No bright, shiny Death Star in sight. After looking at the radioactive carbon and beryllium in tree rings, scientists ruled out a bunch of other possibilities. At first, they considered that it was a smash-up between neutron stars or a neutron star and a black hole. These types of crashes produce a super quick blast of gamma rays without any light show, which lines up best with the evidence. But these kinds of collisions are super rare. Plate thinks it's kinda unlikely that this is the answer. He figures we should only see one of these events in our galaxy about once every million years. So having one just 1,200 years ago seems pretty wild. Scientists are seriously worried about these rare events. If one happened closer to Earth, it could seriously mess up life on our planet. Even if it was thousands of light years away, a similar event today could cause chaos with all the fancy electronic systems we've come to rely on. So it's a good thing those gamma ray bursts are so rare, because if they were more common, Earth might be in for a rough ride. You may think that if our planet could withstand mega radiation blasts, it can easily withstand something less frightening. Let's say grasshoppers. Sorry to say that, but it's not exactly true. Back in 1874, during a hot summer in Kansas, things took a strange turn. Grasshoppers, or should I say locusts, invaded the Great Plains like nobody's business. They came down like a storm, blanketing houses, trees, and even poor trains passing by. These bugs were on a mission to cause chaos. Farmers had to scramble to protect their wells and just about anything else worth saving. Locusts landed everywhere, wreaking havoc on everything in sight. Even poor sheep lost their wool. Locusts even stripped paint off wagons and handles off pitchforks. This is how destructive they were. Livestock tried to fight back by eating them, but there were just too many of these insects. That year, those critters caused about $200 million in crop damage. The locust invasion was so tough, even the US Army stepped in to help. In the end, locusts began to disappear, sparing the plains from further devastation. Natural disasters can be even more unexpected than radiation blasts from space and locust invasions. Check this out. Back in June 2017, a reindeer herder up in northwest Siberia was minding their own business when they suddenly heard a crazy loud blast and saw smoke shooting up from the ground. If that happened to me, I'd need to change my pants. Sorry. Later on, they found this huge hole that was like 23 feet wide and nearly 65 feet deep and was surrounded by chunks of ice and dirt. It turned out that there were over 17 such black holes in the area. They were filled with peaty water and shrouded in mystery. Some folks thought those were sinkholes. Others were sure they were left by top-secret device tests or even a bunch of meteorites. Now, the latest idea is that these holes are actually craters caused by the Arctic warming up and melting the frozen ground. The theory states that as the ground thaws, gas pockets trapped beneath the surface burst through, creating such dramatic holes. Apparently, these eerie craters have been showing up in specific spots in Siberia where ancient geological faults have been leaking out hot natural gas for ages. Combine that with some leftover methane from old lake sediments, and you've got a recipe for some explosive surprises as the planet heats up. Not scared yet? Alright, maybe you're afraid of darkness, huh? If so, you wouldn't like it back in 536. It's the year when the world went through a crazy 18-month period of darkness. A mysterious fog covered Europe, the Middle East, and parts of Asia, blocking out the sun and causing chaos. It was like the Dark Ages, but for real. It turns out that the main culprit behind this fog was a volcanic eruption in Iceland. This eruption spread ash across the northern hemisphere, causing temperatures to drop and crops to fail. People were freezing and starving. It was a mess. Historians from back in the day even talked about how weird it was. The sun looked like the moon. Summers were freezing cold, and even China had summer snow. It was all because of the volcanic ash blocking out the sun. And to make things even worse, this period of darkness sparked the beginning of the bubonic plague in 541. Talk about a rough time to be alive. Let's go back to Siberia real quick. Back in 1908, way out in the wilds of Siberia, an asteroid dropped for an unexpected visit. Today, we know it as the Tunguska asteroid, but it didn't get its name instantly. Local folks only caught a glimpse of the show. A bright fireball streaking across the sky, followed by a massive boom. Trees went flying, fires blazed, and animals weren't too happy about it either. But since the area was so remote, not many folks took notice. For almost 2 decades, nobody bothered to check out the Tunguska site. People had too much on their plates back then. But then, scientists finally made it out there and found evidence of the asteroid's shenanigans. Later in expeditions, they found some spacey microparticles. Fast forward to now, and NASA has a whole planetary defense thing going on. They even sent a mission to test out asteroid deflecting tech. Because who knows when the next cosmic rock will come knocking on our door, right? In the middle of the 19th century, there was one more epic solar storm called the Carrington Event. It may not sound like a big deal to you, but it had pretty rough consequences. The next day after the storm, Earth was hit with this insane geomagnetic storm that threw telegraphs off the rails and brought auroras to the tropics. And it's the place where they normally never show up. Turns out, all this space weather madness started with weird stuff happening on the sun's surface, like sunspots. From these spots, solar flares and other crazy electromagnetic stuff can pop out and mess with our technology. Massive solar storms like this one can shoot out from the sun at speeds of up to 1,800 miles per second. They can contain billions of tons of solar material, complete with a sassy little magnetic field that loves to mess with Earth's magnetic field when they meet. Now, listen closely. We're getting close to the next solar maximum in 2025, so it's a good time to check out the history of the worst solar storms, like the Carrington Event, and take notice. Imagine if a similar storm hit today. An internet apocalypse, anyone? Businesses would be sent offline and we'd be facing some serious damages. Luckily, these mega solar storms don't happen very often. But hey, space weather is tricky to predict, so who knows when the next one will hit?
Floods, tornadoes, tsunamis, hurricanes, yikes. All these natural disasters can get extremely dangerous, but we're kind of familiar with them. But how about a natural disaster that has never happened before, but could occur any moment now? It might be a super eruption. That's what happens when a super volcano erupts. You might know that Yellowstone Park is located on top of a supervolcano. The last massive eruption there happened about 664,000 years ago, and the one before that, approximately 1.3 million years ago. If we do the math, we'll understand that the next eruption might be due anytime soon. There's no strong evidence that the supervolcano is waking up or preparing for an eruption, but what would it be like if it did happen? Months before the eruption, small-scale earthquakes would become more frequent and more powerful in the area. Not long before the eruption, the growing pressure would push up the ground over the volcano, creating a dome. Narrow cracks would open along the edges of this dome. The magma would then start rising toward the surface, and then the eruption would kick off. A massive column of lava and ash would shoot up into the air to a height of over 16 miles. The volcano would keep pumping ash for days on end. The air in that area would heat up to 570 degrees Fahrenheit. For all living creatures, ash fallout would be one of the most dangerous consequences of the eruption. Buildings and trees would start collapsing under the weight of this dense substance. It would only take a couple of days for a 10-foot layer of ash to cover the territory of about 50 miles around the center of the eruption. After the ash got into the stratosphere, the temperatures all over the world would start to drop. The eruption would also be rich in sulfur, and this element is an effective sun blocker. That's why it would soon get so cold that there would be no summer in the whole world for the next several years. The monsoon seasons would change. It would be hard for animals to find food and clean water. Well now, how about a gamma ray burst? You don't stumble across this kind of radiation in your everyday life. A gamma-ray burst occurs when two neutron stars collide. The collapse of a massive star can produce it too. Gamma rays could present a serious danger to Earth. If a gamma-ray burst happened close to our home planet, it could rip our ozone layer away. After that, we would be left unprotected from the sun's ultraviolet radiation. Plus, gamma rays could also produce ground ozone. This kind of ozone could seep into the ocean since it's water-soluble, and that would lead to a mass extinction of marine life. Plants wouldn't survive this disaster either. Now, come to think of it, giant sinkholes could swallow entire communities. One of such sinkholes opened up in the city of New York. It pulled a parked van into the earth. That happened in the summer of 2022. And it wasn't the only sinkhole to appear in that area. Local inhabitants reported about 4,000 sinkholes all over the city. This kind of problem is also very common in Florida, and it's much more serious than it may sound. Sinkholes open all of a sudden, pulling down everything and everyone that happens to be nearby. Sinkholes appear all over the world, which makes them a global problem. They're totally unpredictable and form without warning. Luckily, experts know what causes them. In some areas, there are vast areas of groundwater. But during droughts, this water dries up. This creates large empty caverns, and after heavy rains, the surface over such a cavern can collapse, creating a sinkhole within minutes. Now, what if we came across a wandering black hole? You might know that a black hole is a region in space where gravity is so powerful that not even light can escape its clutches. Luckily, the nearest one to us is 1,500 light-years away. Nothing to worry about, right? Until you find out about wandering black holes. Now, things get definitely way creepier. If such a black hole entered the solar system, Earth would be doomed. We wouldn't stand a chance against this space monster. In 2012, 13 wandering black holes were spotted not so far away from our planet. But worry not. Not far away, in space terms, means around 1 billion light-years away. So we've got some time left. Plus, the possibility of such a disaster is very, very low. Another natural disaster we haven't experienced yet is a mega flood. It's never happened before, but the changes in climate do make for a risky potential. It could start, let's say, in California. This state experienced some really bad flooding in the past. One of such floods stretched up to 60 miles across and 300 miles long. If a similar disaster happened these days, it would cause $1 trillion worth of damage. It would also uproot millions of people. Now let's talk about a hypercane. Judging from the name, this natural disaster might get extreme. A hypercane is a theoretical hurricane of unsurpassed power. It would occur if the ocean became overheated as a result of climate change, or because of a massive volcanic eruption. In any case, these conditions could create a hurricane that would stretch way beyond the lower stratosphere. And as you may guess, regular hurricanes don't do that. The hypercane speed would reach 500 miles per hour. The pressure inside would be low enough not to let the hypercane to wear out as quickly as other hurricanes. The hypercane could last for weeks on end. But the worst thing? It could damage or even destroy part of Earth's ozone layer, and the hole could be the size of the entire North American continent. Now, this disaster did happen before. About 66 million years ago. I bet you know what I'm hinting at. Yep, that very meteor that supposedly wiped out dinosaurs off the face of the Earth. This 7-mile-wide space visitor was traveling at 67,000 miles per hour. As a result of the collision, 75% of all life on the planet disappeared, and winter reigned on Earth for 18 months. Want to know a secret? Meteors strike Earth all the time. Even more of them barely miss our planet. But it's also very hard to predict meteor strikes. Scientists miss a lot of them until they just nearly miss us. That's why experts are working on an early warning system that could prevent disasters. It could make meteor impacts less catastrophic, or at least allow people time to evacuate. It could also be our very own sun that would be responsible for another natural disaster. I'm talking about a massive solar flare. On the scale of damage to society, few catastrophes can compare to this event. It wouldn't destroy buildings like a tsunami or an earthquake. Neither would it end lives in the same way a supervolcano or meteor would. But it would cripple our entire way of life by destroying the whole electronic infrastructure of Earth. The cost of this disaster would reach trillions of dollars. It'd cause other infrastructures to fail: communication, medicine, transportation, banking systems. Those would tumble like dominoes, and it would be incredibly hard to recover them. Earth would be left without electricity for years. There would be no electric light, no computers, no phones. Water supply systems would be out of order. There would be no food in supermarkets. There would be no electricity, and people wouldn't be able to reboot the already broken power grids. In 1859, people all over the world woke up in the middle of the night. It was as light as during the day. The skies were illuminated with auroras, red, green, purple. They appeared even in the regions where no one had seen them before, like the Bahamas, Jamaica, or Hawaii. Telegraphs got electrically charged, even though they were disconnected. In many areas, fires started. That was when technology barely existed. But imagine the avalanche of problems a solar flare could cause today.